Now we're thinking about rotational motion, rotational velocities, rotational accelerations, but many of the things that we do here are very, very similar to things that we've already seen. We have, for instance, a rotational velocity. Instead of measuring how much the location changes as time goes by, rotational velocity measures how much angle a rotating object has swept out in any given amount of time. And then we have acceleration that measures the rate of change of velocity. We also have angular acceleration that measures the rate of change of angular velocity. And our usual symbol for rotational velocity is lowercase Greek letter omega. Our symbol for rotational acceleration, or angular acceleration, is lowercase Greek letter alpha. And I said angular acceleration measures the rate of change of angular velocity, just like this. Just as regular acceleration in meters per second tells you how much velocity change you get in any length of time, angular acceleration in radians per second tells us how much angular velocity, the rate of change of angular velocity, how much angular velocity change there is in any given amount of time. And remember what we said about change in meters per second velocity, we can also say that about change in angular velocity. Change in anything, like angular velocity, is just the final value minus the initial value. So if we add omega initial angular velocity to both sides of the equation, then now here on the left we have initial angular velocity plus delta omega, change in angular velocity, equals final angular velocity. In other words, whenever there's an angular acceleration, whenever there's a change in the angular velocity, and specifically that means that some rotating thing is either spinning faster and faster or slowing down. The spinning is getting slower and slower. Whenever there's some kind of a change in the angular velocity, you can think of that as adding some extra angular velocity onto the angular velocity that you started with in order to give you a different angular velocity at a later time. So, for example, over here we've got imagine, say, a disk, and you're looking at it from above, and the axis of rotation is perpendicular to the blackboard, and it's spinning counterclockwise. Counterclockwise rotation always corresponds to positive angular velocity. And if it's speeding up, that means it's gaining more and more of that same type of angular velocity. The angular velocity is already positive, and you add some more positive angular velocity to it, you get a bigger, stronger, faster positive angular velocity. So you're adding positive angular velocity. Delta omega is positive, which means the angular acceleration is positive. Just as regular acceleration in meters per second has the same sign as delta v, angular acceleration has the same sign as delta omega, the change in angular velocity. So in this case, positive angular velocity and speeding up means more and more positive angular velocity is being added on. Delta omega is positive, so angular acceleration is positive. On the other hand, imagine something rotating counterclockwise and slowing down. Counterclockwise rotation means a positive angular velocity, but it's slowing down, that is, there's less and less of this positive angular velocity as time goes by. So you start with omega initial is some amount of positive angular velocity. Omega final is a smaller amount, which means you had to subtract from the initial angular velocity in order to get the final angular velocity. This is a subtraction. In other words, delta omega is negative. You add a negative number to a positive number, you get a smaller positive number. Less of that positive rotation. In other words, still positive rotation but slowing down. And then imagine things rotating the opposite way. Here, in these two cases, you've got something rotating clockwise, just as counterclockwise rotation was defined as a positive angular velocity. Clockwise rotation is then negative angular velocity. So whether it's speeding up or slowing down, in both these cases the rotation is clockwise, which is a negative angular velocity. Here, you're speeding up. That means you're continuing to rotate with negative velocity, but faster and faster in the negative sense. So this number is negative, and this number is negative, but more negative, or greater in absolute value. Maybe this is -1 rotation per second, and this is -2 rotations per second. Rotating twice as fast as it was here, but -2 means it's rotating in the negative clockwise sense. So to get from -1 to -2, you had to subtract, you had to add more negative angular velocity. And the extra velocity added on is negative angular velocity. The sign of acceleration is the same as the sign of the extra velocity added on. So speeding up with negative rotation means stronger and stronger negative angular velocity, a more and more negative angular velocity, maybe going from minus 10 radians per second to -20 radians per second, something like that. So to get stronger and stronger rotations in the negative direction, you need to add more of the same kind of rotation, negative. And on the other hand, rotating with negative angular velocity but slowing down means as time goes by, you still have negative angular velocity, but less and less of it as time goes by. The initial angular velocity might be something like -10, and the final angular velocity might be something like -5. Here it says 10 goes 10 radians in a second, but negative rotation clockwise, in other words. Now it's still a negative rotation clockwise, but now only 5 radians in a second, spinning slower, but spinning in the negative sense. Well, to get from -10 to -5, you had to add +5. The extra angular velocity added on is positive. And of course, acceleration points in the same direction as the extra velocity added on. So the acceleration is positive. And here we see the same kind of pattern, exactly the same kind of pattern as we saw with regular meters per second velocity and meters per second acceleration. Whenever velocity and acceleration point in the same direction, like they do in this case, both positive, or in this case, both negative, that always corresponds to speeding up. When velocity and acceleration point in opposite directions, here velocity is positive, acceleration is negative. Here velocity is negative, acceleration is positive. whenever velocity and acceleration are opposite, that always corresponds to slowing down. The same pattern that we saw, that we've seen before. Now, similarities extend a little further than that. For regular meters per second accelerations, we know what causes that, a net force. That's what Newton's second law tells us. If there is a net force, that is, if the net force on some object is not zero, then there is acceleration, or acceleration is not zero. Similarly, we know that if there's an angular acceleration, there must be some kind of cause for that as well. Just as it's forces that cause regular meters per second acceleration, there's something else similar to force that causes angular acceleration. If you see something rotating and you see that it has angular acceleration, some angular acceleration other than zero, you know there must be some cause. And the cause of that angular acceleration we call torque. Use Greek letter tau to indicate torque. And just as an object may have a whole bunch of forces, and in order to accelerate, the net result of all those forces has to be non-zero, so too an object might have a bunch of torques acting on it, and in order to get angular acceleration, all those torques have to add up to something other than zero. If the net torque on some object is not zero, then you get angular acceleration. Just as when the net force on something is not zero, you get regular meters per second acceleration. So the question is, what is torque? Torque is a vector, just like force is a vector. For the moment, we'll focus more on the magnitude of the torque. We'll think about direction of the torque a little bit later. And we have a nice handy rule for calculating the magnitude of a torque, and it looks like this. The magnitude of that torque vector, to have a torque you need a force. So one factor here is just the magnitude of the force. And then the next factor is the magnitude of some kind of a displacement vector. We'll talk about what that specifically means in just a minute. And then the third factor is the sine of an angle. So what does that mean? Well, let's imagine a specific example where you're changing the rotational, you're changing the angular velocity of something. Say, opening a door. Before you start pushing on the door is not rotating. It has an angular velocity of zero. Then you start pushing on the door and it rotates about the hinges. Now it's got an angular velocity that is not zero. So the angular velocity changed from zero to something that isn't zero. There was a change in angular velocity. In other words, there was angular acceleration. And it must have been a torque that caused that angular acceleration. And the torque came from the fact that you were pushing on the door with a certain amount of force. Now let's look specifically at what these different factors mean. Here's the door's hinge. Here's the door itself. Here's the doorknob. And now imagine that you're opening the door by pushing on the doorknob. You're applying the force right here. But let's imagine in this case you're not applying the force in the usual sort of way, pushing perpendicular to the door, but let's say you're pushing at an angle, like that. Your push is like that. It'll still make the door open. So extend that line of force just a little bit. The line of force will be related to that angle in the sine, its sine factor. This factor here, a displacement, is a displacement that starts from some kind of a reference point and takes you to the point where the force is applied, which is right here in this case. The reference point for torques, as you saw in the reading, can be anywhere. It doesn't matter where you define the reference point. It's simplest and easiest to understand if you put the reference point at the axis of rotation, usually. So let's do that and see what happens. So reference point right here at the hinge, which is going to be the axis of rotation when the door starts opening. And then that displacement vector is a displacement that takes you directly from the reference point to the point where the force is applied. So in this particular case, the magnitude of the displacement vector is just the width of the door. And then that sine factor, the angle in that sine factor is an angle between the displacement direction and the force direction. So let's compare some different torques by applying this force differently to the door. First case, we'll just open the door normally, apply the force right there. So in this case, the magnitude of torque in the first case is just the magnitude of that force times the magnitude of the displacement vector. Will for all these cases, we want to leave the reference point the same so we can actually compare one case to another. And we'll always keep the reference point right at the hinge, right at the axis of rotation. So the displacement vector then takes us from the reference point at the hinge to where the force is applied, way out there. And so the magnitude of that displacement vector is just the width of the door. Let's call it W for width. And then sine of the angle between the displacement vector, displacement direction, and the force direction. Well, in this case, displacement and force are perpendicular to each other. So you've got sine of 90 degrees. Sine of 90 degrees is just plain 1. So the magnitude of that torque is just magnitude of the force times width of the door. Now, imagine case 2 here. Again, I apply the force to the doorknob, but now I push at an angle. Say push at an angle like that. Force is the same strength, but now I'm just pushing in a different direction. And the displacement vector is still taking you from the hinge all the way to the doorknob, from the reference point to the point where the force is applied. So the magnitude of the displacement vector is still width of the door. And now the angle between the force direction and the displacement direction, let's say it's 45 degrees instead of 90 degrees in the previous example. So now in this case, the magnitude of torque in the second case is same force, so same magnitude, same displacement vector, so that factor is still equal to the width of the door. Now the third term is now sine of the angle between force direction and displacement direction, that's sine of 45 degrees. Ask your calculator what the sine of 45 degrees is, and your calculator will tell you that it's about 0.71. So the magnitude of this torque is about 0.71 times magnitude of the force times width, or about 0.71 times the magnitude of the first torque. Torque 2 is smaller than the first torque. Now, let's look at a third example. Let me just write these all up here for reference so we can compare them in the end. Third example, very similar to 2. Same reference point at the hinge. Again, you apply the force at the doorknob, push on the doorknob, but now at different angle than before, like that. Displacement is still from the same reference point to the point where the force is applied. So displacement vector is still from the hinge to the doorknob. Force is still the same magnitude, but now it's pushing in a different direction. That is, in this case, the angle between the displacement direction and the force direction is 30 degrees. So torque in the third case here is magnitude of the same force, same amount of force, same magnitude because of displacement vector. Displacement vector is still from the hinge to the doorknob, and so the magnitude of that displacement is still the width of the door. And now the third factor is sine of the angle between displacement direction and force direction. That's sine of 30 degrees. Sine of 30 degrees turns out to equal 1/2. So torque 3 is 1/2 magnitude of force times width of the door. Now, fourth example, number 4, we'll go back to pushing perpendicular to the door, like in case 1. There's the doorknob, and again we're going to push perpendicular with the same amount of force, but now we're not going to push on the doorknob, we're going to push right in the middle of the door. Same amount of force and perpendicular to the door, but now we're pushing in the middle instead of out at the end where the doorknob is. So now the displacement vector takes us from the reference point to the point where the force is applied. The force is applied right here in the middle of the door. So the magnitude of this displacement vector is just this distance, which is half of the width of the door. And then the angle between the force direction and the displacement direction is 90 degrees. Now, just like in case 1, force and displacement are perpendicular. So in the fourth case, the torque, the magnitude of the torque is magnitude of the force, half the length, half the width of the door times sine 90 degrees, and of course sine 90 degrees is just 1. So the magnitude of the torque in this case is just 1/2 force width. And one last example. Now let's say there's the door, case 5. We'll keep the reference point right here, but now imagine that you apply that same F, newtons of force, right to the reference point. In that case, what's that displacement vector like? Remember, the displacement takes you from the reference point to the point where the force is applied, but here's the reference point, and here's the point where the force is applied. Same place. So the distance between the reference point and the point where the force is applied is zero distance. They're the same point. That displacement vector in the torque equation is zero. So in this case, the magnitude of that torque is zero. That makes sense. You can't make the door rotate. You can't open the door, obviously, if you're pushing at the hinge. And this is why, because if you push at the hinge, you get zero torque. And you need torque in order to change the rotational state of the door, change it from not rotating to rotating. So in this case, the ranking of those torques would be number 1 is the biggest, and then number 2 is the next largest, and then 3 and 4 are equally large. They're both half the magnitude of number 1, and then torque 5 is the smallest, has the smallest magnitude. It has a magnitude of 0. Everything that we do with torques is based on that one equation. Magnitude of a torque is magnitude of the force that you need in order to have a torque, and then magnitude of the displacement vector that takes you from a reference point to the force. And as we saw in the case of torque 5, in order to have a torque, the reference point and the place where the force is applied have to be different places, so that the distance between the reference point and the point where the force is applied is not 0. And then sine of the angle between the displacement direction and the force direction. Everything we'll be doing with torques from now on is just a variation, on that idea, an application of that idea. Even though there's not a lot of stuff to think about in this equation, it actually does take some getting used to, but you'll have plenty of chances to get used to it practicing in class.